This is the first of several lessons on uncertainty and error. In this lesson, we're going to talk about uncertainty in observed quantities, meaning uncertainty in our measurements. Your objectives are we're going to be able to define and distinguish precision and accuracy, give examples of random and systematic error, outline rules for reporting the uncertainty in a single measurement, and also apply a rule for estimating the uncertainty in the mean of repeated measurements. First, let's talk about precision and accuracy. Precision means how reproducible our measurements are. In other words, how close our repeated measurements are to each other. Whereas accuracy refers to how close our measurements are to the accepted reference value. So, for example, let's say that we were trying to measure acceleration due to gravity and we kept getting a value of 7 meters per second squared. That would be a relatively inaccurate experiment compared to one that got a value of 10 meters per second squared. Often precision and accuracy are shown like this. On the right-hand side, you see a target. Here, the shots are not very accurate. They're not close to the target, and they're also not very precise. They're not stacked one on top of each other. As opposed to down here, while they're still not accurate, they're not close to the target, the accepted reference value in this case. They are close to each other, so they're precise. What we want, of course, is something that is accurate and precise for our experiment. Another way of thinking about this is here we see the probability density on the side. That means basically where our shots are landing. And if the accepted reference value is right there, then how far our measurements are, these are a distribution of our measurements, how far the mean of our measurements are, this distance is a measure of accuracy, and the spread of our measurements is a measure of precision. You can kind of think of this as looking at the targets from the side, so that each time a shot lands at the target, it builds up the height of this curve. Now that we've got that terminology, let's turn to talking about random and systematic error. I often refer to them as random uncertainty and systematic bias, just to help keep them straight. You'll see what I mean in a moment. So with random uncertainty, the values that we are getting for our measurements vary both upwards and downwards from the true value. To go back to our finding acceleration due to gravity experiment, let's imagine that we're getting values of 9.6, 10, 9.4, 11. The values that we're getting are scattered in both directions. And this could be the result of several things. It could be a result of our measurement instrument and difficulty reading it. It could be something in the environment. For example, let's say we're finding the mass of something and there are little air currents in the room, and those air currents on the balance are making the values both too high and too low, and you've probably seen that when reading a balance that the values read up and down. Now, if an experiment has relatively little random uncertainty, then the values will tend to stack up one on top of the other, and therefore the experiment is precise. Now, because the values scatter both upwards and downwards, we can address random uncertainty by repeating our observations, repeating our experiment, and then averaging the results. And that works because, on average, the values that are too big should cancel out with the values that are too small when we do the average. So that's why we repeat our trials and average them to deal with random uncertainty. In contrast, systematic error or systematic bias is when all of our values are skewed in one direction only. For example, again, with our acceleration due to gravity experiment, we were getting, let's say, 11, 11, 11, 11 meters per second squared as our results. Now, that can't be dealt with by averaging because all of the values are either too big or too small. Systematic bias could result from things like calibration problems, or let's say you're measuring something with a stopwatch and you're always just a bit too slow in stopping the stopwatch, so your reaction time, those might skew things all in one direction. Again, because all of the values are skewed only in one direction, we can't actually deal with them by repeating and averaging. We actually just have to go back and redesign or relook at our experiment and redo it. If there is relatively little systematic bias in an experiment, then we say that the experiment is accurate because the results that we're going to get are not going to be skewed. They're going to be close to the true accepted value. So that's random uncertainty and systematic bias. Now let's look at how we judge and report uncertainty in a single measurement. First, uncertainty is reported using plus or minus. So for example, you might see something like 54.72 plus or minus 0.01 grams. We use a plus or minus here, and then we put the units at the end of the whole thing. So how do we figure out what this uncertainty should be? First, let's talk about the limitations of the instrument itself. There are a couple of different guidelines that we can follow. With a digital instrument, you might see a reading something like this on a balance. So we would read that as 3.36 plus or minus 0.01 grams. The general rule for digital readouts is that we're going to use plus or minus the smallest scale division. I'm going to write that as SSD, the smallest scale division. This reads to 1/100th of a gram, so my limitation of my instrument uncertainty is hundredths of a gram. In contrast, the rule for analog instruments, like the ruler that I've shown here, is plus or minus half the smallest scale division. So for example, this object we might read as it looks like it's a bit more than halfway, so let's say that's 5.6 centimeters plus or minus 0.5 centimeters. So for analog instruments, the rule is plus or minus half the smallest scale division. Now, just because you've got the limitations of the instrument as the smallest scale division or half the smallest scale division, that doesn't mean that's what you should report as your uncertainty in your single measurement. Because there may be other uncertainties arising from limitations of you, the observer yourself, or the way that you're able to do the observation. Let's say, using this example again, when you look at this from different angles, the object and the ruler might line up a bit differently, and if that's hard to eliminate, that's going to cause more uncertainty. That's an effect called parallax error. To go back to the example that we were using before with a stopwatch, your reaction time is going to add some uncertainty to your measurements as well. Or let's say you're trying to measure the top of a bounce of a ball by eye, and you're trying to figure out on a moving ball, when does it get to exactly this height? That's going to be another source of error that's attributable to the observer and the observations you're making, and it's not just going to be the smallest scale division or half the smallest scale division on the instrument. So just be careful about that. There can be a temptation once you've learned these guidelines about instrument uncertainty to quote that and ignore other sources of uncertainty that are creeping into your experiment. So once you've decided on an uncertainty, you should report the uncertainty, this value over here, to one significant figure in general, maybe two on occasion, but generally to one. And then once you've got that, you're going to round the value, the number before the plus or minus, to the same place value. In other words, for the example given here, 45.2 plus or minus 0.1 centimeters is correct because this is to one significant figure, and then it's to the 10th decimal place, so this is also to the 10th decimal place. These two are wrong. Here we've got something to the 1000th decimal place. It's correctly to one significant figure, but once this is to the thousandths, this needs to be to the thousandths as well. Or if this is to the tenths, this needs to be to the tenths as well. Similarly here, we've got a mismatch of place values, so those are both incorrect. Again, report your uncertainty to one significant figure, and once you've got that, then go and round the value before the plus or minus to the same place value. So that's how to report your uncertainty in a single measurement. But how about when you repeat measurements? Remember, we're repeating measurements in order to try to deal with random uncertainty. Let's say you time a ball falling from height and you get these 5 times. We're going to average them, and when we average them, we get this out of our calculator. Now we know that that's too many decimal places, too many significant figures, but we're going to leave the rounding of that for a moment until we decide on the uncertainty. Then we're going to use the process above. So how do we report the uncertainty in this mean? There are more involved statistical techniques like standard deviation, which you can investigate, but an acceptable approach, and one that the IB uses, is to just use half the max value minus the min value. In other words, half the range, if the range is the maximum minus the minimum value. So in this example, we would take half by 5.05 seconds minus 4.72 seconds, our max and min values. That gives us 0.165, or rounded to our one significant figure, 0.2 seconds. So I know that I'm going to have an uncertainty of plus or minus 0.2 seconds. Now I need to round this value so that it has tenths as the last decimal place. So I report 4.9 plus or minus 0.2 seconds as my final answer. So that's an introduction to random and systematic error and uncertainty in a single measurement and in the mean of repeated measurements.